one of the questions that we want to ask ourselves is, how can we calculate or mathematically determine heat change? Well, the simple answer to that is through temperature. So what is the role of temperature in all of this? Temperature measures the average kinetic energy of molecules, which means that when all movement of molecules stops, that will be the lowest temperature that we could obtain, theoretically, as absolute zero. In fact, scientists did reach there and measured it to be negative 273 degrees Celsius. They also defined a Kelvin scale, which shares the same incremental scaling as degrees Celsius. So Kelvin eventually becomes the SI unit of temperature, and the conversion is as follows. Okay. If room temperature is 25 degrees, on the Kelvin scale, it would be 298 K. And the absolute zero is the Kelvin zero, which also can be calculated as 0K, okay? So when a substance is given energy, the particles within it will start to move or vibrate more, like this, okay? So this will result in a change in temperature, okay? More kinetic energy, higher temperature. The question for us then is, how do we quantify this? So we define heat capacity as the energy needed to increase the temperature of a certain amount of substances by 1 degree. As you can imagine, let's say from life experience, it would intuitively take a lot more energy to warm up a glass of water compared to what it takes to warm up the same amount of bread. By same amount of bread, I'm referring to bread that weighs the same as water. You can think like bread takes about 20 seconds when water might take, maybe a minute or two to actually warm up to the same degree, okay? So that suggests that every substance has their own specific heat capacity that actually could be measured. And here's a table for it. You will notice that the specific heat capacity of water is particularly high, which speaks to the intermolecular forces among water molecules that tended to be more stronger compared to in other substances. Okay. Mathematically, we have this formula, Q equals to Cm delta T, to calculate the heat required of a system to change its temperature. So it has something to do with the constant, the specific heat capacity constant, which depends on the nature of that particular substance, multiplied by the mass, because if you imagine to heat up a small loaf of bread versus a huge loaf of baguette will require a different amount of energy. Okay. Also, it comes down to the amount of temperature that you actually do want to change. Okay. So the quantity and the units is where we actually want to pay attention to when we're doing the calculation. Also, the substance-specific constant value for water is given in our data book. Let's see an example. A sample of burning food is used to heat 100 ml of water. Let's calculate the heat energy in kilojoules that has been transferred if the temperature of water increases from 18.5 degrees to 44 degrees. Okay. So we know that the amount of heat required has something to do with the amount of water, the constant, and the temperature change. Here, the temperature change is 25.5 degrees. We can write it in kelvins as well. Remember, they have the same incremental scale, which means our delta T will always be the same number, whether we calculate it in kelvins or if we just use degrees. The mass of water here to be heated up, it's 100 mils, and water's density is 1 grams per mil, so it's essentially 100 grams. Then the heat can be calculated to be 10,659 joules.